Electrochemistry, Electrochemical cells. We had studied the construction and functioning of Daniell cell. This cell converts the chemical energy liberated during the following redox reaction to electrical energy. Zn solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus Cu solid, that is equation 1, and has an electrical potential equal to 1.1 volt when the concentration of Zn2 plus and Cu2 plus ions is unity, that is 1 mole per decimeter cube. Such a device is called a galvanic or a voltaic cell. If an external opposite potential is applied in the galvanic cell and increased slowly, then we find that the reaction continues to take place till the opposing voltage reaches the value of 1.1 volt, and the reaction doesn't stop altogether and doesn't stop current flows through the cell. Any further increase in the external potential again starts the reaction, but in the opposite direction. It now functions as an electrolytic cell, a device for using electrical energy to carry non-spontaneous chemical reactions. Both types of cells are quite important. When E external is equal to 1.1 volt, 1. No flow of electrons or current. 2. No chemical reaction. When E external is greater than 1.1 volt, 1. Electrons flow from Cu to Zn and current flows from Zn to Cu. 2. Zinc is deposited at the zinc electrode and copper dissolves at copper electrode. Galvanic cells. A galvanic cell is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy. In this device, the Gibbs energy of the spontaneous redox reaction is converted into electrical work, which may be used for running a motor or other electrical gadgets like heater, fan, geyser, etc. Daniell cell discussed earlier is one cell in which the following redox reaction occurs. Zn solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus Cu solid. This reaction is a combination of two half reactions whose addition gives the overall cell reaction. 1. Cu2 plus 2 electron minus, it gives Cu solid, that is reduction half reaction, that is equation 2. 2. Zn solid, it gives Zn2 plus aqueous plus 2 electron minus, that is oxidation half reaction, that is equation 3. These reactions occur in two different portions of the Daniell shell. The reduction half reaction occurs on the copper electrode while the oxidation half reaction occurs on the zinc electrode. These two portions of the cell are also called half cells or redox couples. The copper electrode may be called the reduction half cell and the zinc electrode the oxidation half cell. We can construct innumerable number of galvanic cells on the pattern of Daniell cell by taking combinations of different half cells. Each half cell consists of a metallic electrode dipped into an electrolyte. The two half cells are connected by a metallic wire through a voltmeter and a switch externally. The electrolytes of the two half cells are connected internally through a salt bridge. Sometimes both the electrodes dip in the same electrolyte solution, and in such cases we do not require a salt bridge. At each electrode-electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, metal atoms of the electrode have a tendency to go into the solution as ions and leave behind the electrons at the electrode, trying to make it negatively charged. At equilibrium, there is a separation of charges, and depending on the tendencies of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentrations of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. According to IUPAC convention, Standard reduction potentials are now called standard electrode potentials. In a galvanic cell, the half cell in which oxidation takes place is called anode, and it has a negative potential with respect to the solution. The other half cell in which reduction takes place is called cathode, and it has a positive potential with respect to the solution. Thus, there exists a potential difference between the two electrodes, and as soon as the switch is in the on position, the electrons flow from negative electrode to positive electrode. The direction of current flow is opposite to that of electron flow. The potential difference between the two electrodes of a galvanic cell is called the cell potential and is measured in volts. The cell potential is the difference between the electrode potentials, that is, reduction potentials of the cathode and anode. It is called the cell electromotive force, that is, EMF of the cell when no current is drawn through the cell. It is now an accepted convention that we keep the anode on the left and the cathode on the right while representing the galvanic cell. A galvanic cell is generally represented by putting a vertical line between metal and electrolyte solution and putting a double vertical line between the two electrolytes connected by a salt bridge. Under this convention, the EMF of the cell is positive and is given by the potential of the half cell on the right hand side minus the potential of the half cell on the left hand side, that is, E cell is equal to E right minus E left. This is illustrated by the following example. Cell reaction Cu solid plus 2Ag plus aqueous, it gives Cu2 plus aqueous plus 2Ag solid, that is equation 4. Half cell reactions cathode, that is reduction, 2Ag plus aqueous plus 2 electron minus, it gives 2Ag solid, that is equation 5. Anode, that is oxidation, Cu solid, it gives Cu2 plus aqueous plus 2 electron minus, that is equation 6. It can be seen that sum of 5 and 6 leads to overall reaction 4 in the cell, and that silver electrode acts as a cathode and copper electrode acts as an anode. The cell can be represented as Cu solid, change in state, Cu2 plus aqueous, junction between half cells, that is salt bridge, Ag plus aqueous, change in state, Ag solid, and we have E cell is equal to E right minus E left is equal to E Ag plus change in state Ag minus E Cu2 plus change in state Cu, that is equation 7. Measurement of electrode potential. The potential of individual half cell cannot be measured. We can measure only the difference between the two half cell potentials that gives the EMF of the cell. If we arbitrarily choose the potential of one electrode, that is half cell, then that of the other can be determined with respect to this. According to convention, a half cell called standard hydrogen electrode represented by Pt solid, change in state, H2 gaseous, change in state, H plus aqueous, is assigned a zero potential at all temperatures corresponding to the reaction. H plus aqueous plus E minus, it gives 1 upon 2 H2 gaseous. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. The concentration of both the reduced and oxidized form of hydrogen is maintained at unity. This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. At 298 Kelvin, the EMF of the cell, standard hydrogen electrode, junction between half cells, that is salt bridge, second half cell, constructed by taking standard hydrogen electrode as anode, that is reference half cell, and the other half cell as cathode, gives the reduction potential of the other half cell. If the concentrations of the oxidized and the reduced forms of the species in the right hand half cell are unity, then the cell potential is equal to standard electrode potential E standard electrode potential R of the given half cell. E standard electrode potential is equal to E standard electrode potential R minus E standard electrode potential L, as E standard electrode potential L for standard hydrogen atom is 0. E standard electrode potential is equal to E standard electrode potential R minus 0 is equal to E standard electrode potential R. The measured EMF of the cell PT solid, change in state H2 gaseous 1 bar, change in state H plus aqueous 1 molar, junction between half cells, that is salt bridge, Cu2 plus aqueous 1 molar, change in state Cu, is 0.34 volt, and it is also the value for the standard electrode potential of the half cell corresponding to the reaction Cu2 plus aqueous 1 molar plus 2E minus, it gives Cu solid. Similarly, the measured EMF of the cell PT solid, change in state H2 gaseous 1 bar, change in state H plus aqueous 1 molar, junction between half cells, that is salt bridge, Zn2 plus aqueous 1 molar, change in state Zn, is minus 0.76 volt, corresponding to the standard electrode potential of the half cell reaction Zn2 plus aqueous 1 molar plus 2E minus, it gives Zn solid. The positive value of the standard electrode potential in the first case indicates that Cu2 plus ions get reduced more easily than H plus ions. The reverse process cannot occur, that is, hydrogen ions cannot oxidize Cu, that is, or alternatively we can say that hydrogen gas can reduce copper ion under the standard conditions described above. Thus, Cu does not dissolve in HCl. In nitric acid, it is oxidized by nitrate ion and not by hydrogen ion. The negative value of the standard electrode potential in the second case indicates that hydrogen ions can oxidize zinc, or zinc can reduce hydrogen ions. In view of this convention, the half reaction for the Daniell cell can be written as left electrode Zn solid, it gives Zn2 plus aqueous 1 molar plus 2E minus. Right electrode Cu2 plus aqueous 1 molar plus 2E minus, it gives Cu solid. The overall reaction of the cell is the sum of above two reactions, and we obtain the equation Zn solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus Cu solid. EMF of the cell is equal to E standard electrode potential cell is equal to E standard electrode potential R minus E standard electrode potential L is equal to 0.34 volt minus 0.76 volt is equal to 1.10 volt. Sometimes metals like platinum or gold are used as inert electrodes. They do not participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrons. For example, PT is used in the following half cells: hydrogen electrode PT solid, change in state H2 gaseous, change in state H plus aqueous, with half cell reaction H plus aqueous plus E minus, it gives 1 upon 2 H2 gaseous. Bromine electrode PT solid, change in state Br2 aqueous, change in state Br minus aqueous, with half cell reaction 1 upon 2 Br2 aqueous plus E minus, it gives Br minus aqueous. The standard electrode potentials are very important and we can extract a lot of useful information from them. The values of standard electrode potentials for some selected half cell reduction reactions are given in table. If the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable compared to hydrogen gas. Similarly, If the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. It can be seen that the standard electrode potential for fluorine is the highest in the table, indicating the fluorine gas F2 has the maximum tendency to get reduced to fluorine ions, that is F-, and therefore fluorine gas is the strongest oxidizing agent and fluorine ion is the weakest reducing agent. Lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent, while the lithium metal is the most powerful reducing agent in an aqueous solution. It may be seen that as we go from top to bottom in table, the standard electrode potential decreases, and with this decreasing the oxidizing power of the species on the left and increasing the reducing power of the species on the right hand side of the reaction. Electrochemical cells are extensively used for determining the pH of solutions, solubility product, equilibrium constant, and other thermodynamic properties, and for potentiometric titrations. Nernst equation. The concentration of all the species involved in the electrode reaction is unity. This need not to be always true. Nernst showed that for the electrode reaction, Mn plus aqueous plus Ne minus, it gives M solid. The electrode potential at any concentration measured with respect to the standard hydrogen electrode can be represented by E Mn plus M is equal to E standard electrode potential Mn plus M minus RT upon Nf log of M upon Mn plus. But concentration of solid M is taken as unity, and we have E Mn plus M is equal to E standard electrode potential Mn plus M minus RT upon Nf log of 1 upon Mn plus. That is equation 8. E standard electrode potential Mn plus M has already been defined. R is gas constant, that is 8.314 joule per Kelvin mole. F is Faraday constant, that is 96,487 coulomb per mole. T is temperature in Kelvin, and Mn plus is the concentration of the species Mn plus. In Daniel's shell, the electrode potential for any given concentration of Cu2 plus and Zn2 plus ions we write for cathode E Cu2 plus Cu is equal to E standard electrode potential Cu2 plus Cu minus RT upon 2F log of 1 upon Cu2 plus aqueous, that is equation 9. For anode, E Zn2 plus Zn is equal to E standard electrode potential Zn2 plus Zn minus RT upon 2F log of 1 upon Zn2 plus aqueous, that is equation 10. The cell potential E cell is equal to E Cu2 plus Cu minus E Zn2 plus Zn is equal to E standard electrode potential Cu2 plus Cu minus RT upon 2F log of 1 upon Cu2 plus aqueous minus E standard electrode potential Zn2 plus Zn minus RT upon 2F log of 1 upon Zn2 plus aqueous is equal to E standard electrode potential Cu2 plus Cu minus E standard electrode potential Zn2 plus Zn minus RT upon 2F log of 1 upon Cu2 plus aqueous minus log of 1 upon Zn2 plus aqueous. E shell is equal to E standard electrode potential cell minus RT upon 2F log of Zn2 plus upon Cu2 plus, that is equation 11. It can be seen that E shell depends on the concentration of both Cu2 plus and Zn2 plus ions. It increases with increase in the concentration of Cu2 plus ions and decrease in the concentration of Zn2 plus ions. By converting the natural logarithm in equation 11 to the base 10 and substituting the values of R, F and T is equal to 298 Kelvin, it reduces to E shell is equal to E standard electrode potential cell minus 0.059 upon 2 log of Zn2 plus upon Cu2 plus, that is equation 12. We should use the same number of electrons, that is N, for both the electrodes, and thus for the following cell Ni solid, change in state Ni2 plus aqueous, junction between half cells, that is salt bridge Ag plus aqueous, change in state Ag. The cell reaction is Ni solid plus 2Ag plus aqueous, it gives Ni2 plus aqueous plus 2Ag solid. The Nernst equation can be written as E shell is equal to E standard electrode potential cell minus RT upon 2F log of Ni2 plus upon Ag plus square. And for a general electrochemical reaction of the type A plus B in the presence of Ne minus, it gives Cc plus Dd. Nernst equation can be written as E cell is equal to E standard electrode potential cell minus RT upon NF log of Q is equal to E standard electrode potential cell minus RT upon NF log of C raised to C into D raised to D upon A raised to A into B raised to B, that is equation 13. Example 1. Represent the cell in which the following reaction takes place. Mg solid plus 2Ag plus 0.0001 molar, it gives Mg2 plus 0.130 molar plus 2Ag solid. Calculate its E shell if E standard electrode potential cell is equal to 3.17 volt. Solution. The cell can be written as Mg, change in state Mg2 plus 0.130 molar, junction between half cells, that is salt bridge Ag plus 0.0001 molar, change in state Ag. E shell is equal to E standard electrode potential cell minus RT upon 2F log of Mg2 plus upon Ag plus square is equal to 3.17 volt, 3.17 volt minus 0.059 volt upon 2 log of 0.130 upon 0.0001 square is equal to 3.17 volt minus 0.21 volt is equal to 2.96 volt. Equilibrium constant from Nernst equation. If the circuit in Daniell cell is closed, then we note that the reaction Zn solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus Cu solid, that is equation 1. Takes place as time passes. The concentration of Zn2 plus keeps on increasing while the concentration of Cu2 plus keeps on decreasing. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. After some time, we shall note that there is no change in the concentration of Cu2 plus and Zn2 plus ions, and at the same time, voltmeter gives 0 reading. This indicates that equilibrium has been attained. In this situation, the Nernst equation may be written as E shell is equal to 0 is equal to E standard electrode potential cell minus 2.303 RT upon 2F log of Zn2 plus upon Cu2 plus, or E standard electrode potential cell is equal to 2.303 RT upon 2F log of Zn2 plus upon Cu2 plus. But at equilibrium, Zn2 plus upon Cu2 plus is equal to Kc for the reaction 1, and at T is equal to 298 Kelvin, the above equation can be written as E standard electrode potential cell is equal to 0.059 volt upon 2 log of Kc is equal to 1.1 volt, that is E standard electrode potential cell is equal to 1.1 volt. Log of Kc is equal to 1.1 volt into 2 upon 0.059 volt is equal to 37.288. Kc is equal to 2 into 10 raised to 37 at 298 Kelvin. In general, E standard electrode potential cell is equal to 2.303 RT upon NF log of Kc, that is equation 14. Thus, equation 14 gives a relationship between equilibrium constant of the reaction and standard potential of the cell in which that reaction takes place. Thus, equilibrium constants of the reaction, difficult to measure otherwise, can be calculated from the corresponding E standard electrode potential value of the cell. Example 2. Calculate the equilibrium constant of the reaction Cu solid plus 2Ag plus aqueous. It gives Cu2 plus aqueous plus 2Ag solid. E standard electrode potential cell is equal to 0.46 volt. Solution: E standard electrode potential cell is equal to 0.059 volt upon 2 log of Kc is equal to 0.46 volt, or log of Kc is equal to 0.46 volt into 2 upon 0.059 volt is equal to 15.6. Kc is equal to 3.92 into 10 raised to 15. Electrochemical cell and Gibbs energy for the reaction. Electrical work done in 1 second is equal to electrical potential multiplied by total charge passed. If we want to obtain maximum work from a galvanic cell, then charge has to be passed reversibly. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy, and therefore, if the EMF of the cell is E and NF is the amount of charge passed and delta Rg is the Gibbs energy of the reaction, then delta Rg is equal to minus NF E shell, that is equation 15. It may be remembered that E shell is an intensive parameter, but delta Rg is an extensive thermodynamic property and the value depends on N. Thus, if we write the reaction Zn solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus Cu solid. Delta Rg is equal to minus 2F E shell. But when we write the reaction 2Zn solid plus 2Cu2 plus aqueous, it gives 2Zn2 plus aqueous plus 2Cu solid. Delta Rg is equal to minus 4F E shell. If the concentration of all the reacting species is unity, then E shell is equal to E standard electrode potential cell, and we have delta Rg standard electrode potential is equal to minus NF E standard electrode potential cell, that is equation 16. Thus, from the measurement of E standard electrode potential cell, we can obtain an important thermodynamic quantity, delta Rg standard electrode potential, standard Gibbs energy of the reaction. From the latter, we can calculate equilibrium constant by the equation delta Rg standard electrode potential is equal to minus RT log of K. Example 3. The standard electrode potential for Daniell cell is 1.1 volt. Calculate the standard Gibbs energy for the reaction. Zn solid plus Cu2 plus aqueous, it gives Zn2 plus aqueous plus Cu solid. Solution: delta Rg standard electrode potential is equal to minus NF E standard electrode potential cell. N in the above equation is 2. F is equal to 96,487 coulomb per mole, and E standard electrode potential cell is equal to 1.1 volt. Therefore, delta Rg standard electrode potential is equal to minus 2 into 1.1 volt into 96,487 coulomb per mole is equal to minus 21,227 joule per mole is equal to minus 21.227 kilojoule per mole. Conductance of electrolytic solutions. The electrical resistance is represented by the symbol R and it is measured in ohm, which in terms of SI base units is equal to kilogram meter square or Siemens cube area square. It can be measured with the help of a Wheaton bridge. The electrical resistance R of any object is directly proportional to its length L and inversely proportional to its area of cross section A. That is, R is proportional to L upon A, or R is equal to rho into L upon A. That is equation 17. The constant of proportionality rho is called resistivity, that is specific resistance. Its SI units are ohm meter, and quite often its submultiple ohm centimeter is also used. IUPAC recommends the use of term resistivity over specific resistance, and hence in the rest of the book we shall use the term resistivity. Physically, the resistivity for a substance is its resistance when it is 1 meter long and its area of cross section is 1 meter square. It can be seen that 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01 ohm meter. The inverse of resistance R is called conductance G, and we have the relation G is equal to 1 upon R is equal to A upon rho L is equal to K into A upon L. That is equation 18. The SI unit of conductance is Siemens, represented by the symbol S, and is equal to ohm inverse. That is also known as mho or ohm inverse. The inverse of resistivity, called conductivity, that is specific conductance, is represented by the symbol K, that is kappa. IUPAC has recommended the use of term conductivity over specific conductance, and hence we shall use the term conductivity in the rest of the book. The SI units of conductivity are Siemens per meter, but quite often K is expressed in Siemens per centimeter. Conductivity of a material in Siemens per meter is its conductance when it is 1 meter long and its area of cross section is 1 meter square. It may be noted that 1 Siemens per centimeter is equal to 100 Siemens per meter. The values of conductivity of some selected materials at 298.15 Kelvin. Material conductivity Siemens per meter. Material conductivity Siemens per meter. Conductors aqueous solutions. Conductors sodium. Conductivity 2.1 into 10 raised to 3. Aqueous solutions pure water. Conductivity 3.5 into 10 raised to minus 5. Conductors copper. Conductivity 5.9 into 10 raised to 3. Material 0.1 molar HCl. Conductivity 3.91. Conductors silver. Conductivity 6.2 into 10 raised to 3. Aqueous solutions 0.01 molar KCl. Conductivity 0.14. Conductors gold. Conductivity 4.5 into 10 raised to 3. Aqueous solutions 0.01 molar NaCl. Conductivity 0.12. Conductors iron. Conductivity 1.0 into 10 raised to 3. Aqueous solutions 0.1 molar HAC. Conductivity 0.047. Conductors graphite. Conductivity 1.2 into 10. Aqueous solutions 0.01 molar HAC. Conductivity 0.016. Material insulators. Conductivity Siemens per meter. Material semiconductors. Conductivity Siemens per meter. Insulators glass. Conductivity 1.0 into 10 raised to minus 16. Semiconductors CuO. Conductivity 1 into 10 raised to minus 7. Insulators Teflon. Conductivity 1.0 into 10 raised to minus 18. Semiconductors Si 1.5 into 10 raised to minus 2. Semiconductors GE. Conductivity 2.0. It can be seen from table that the Magnitude of conductivity varies a great deal and depends on the nature of the material. It also depends on the temperature and pressure at which the measurements are made. Materials are classified into conductors, insulators, and semiconductors depending on the magnitude of their conductivity. Metals and their alloys have very large conductivity and are known as conductors. Certain non-metals like carbon black, graphite, and some organic polymers are also electronically conducting. Substances like glass, ceramics, etc. having very low conductivity are known as insulators. Substances like silicon, doped silicon, and gallium arsenide having conductivity between conductors and insulators are called semiconductors and are important electronic materials. Certain materials called superconductors by definition have zero resistivity or infinite conductivity. Earlier, only metals and their alloys at very low temperature, that is 0 to 15 Kelvin, were known to behave as superconductors. But nowadays, number of ceramic materials and mixed oxides are also known to show superconductivity at temperatures as high as 150 Kelvin. Electrical conductance through metals is called metallic or electronic conductance and is due to the movement of electrons. The electronic conductance depends on 1. The nature and structure of the metal, 2. The number of valence electrons per atom, 3. Temperature, that is, it decreases with increase of temperature. As the electrons enter at one end and go out through the other end, the composition of the metallic conductor remains unchanged. The mechanism of conductance through semiconductors is more complex. Even very pure water has small amounts of hydrogen and hydroxylic ions, that is approximately 10 raised to minus 7 molar, which lend it very low conductivity, that is 3.5 into 10 raised to minus 5 Siemens per meter. When electrolytes are dissolved in water, they furnish their own ions in the solution, hence its conductivity also increases. The conductance of electricity by ions present in the solutions is called electrolytic or ion conductance. The conductivity of electrolytic, that is ionic solutions, depends on 1. The nature of the electrolyte added, 2. Size of the ions produced and their solvation, 3. The nature of the solvent and its viscosity, 4. Concentration of the electrolyte, 5. Temperature, that is, it increases with the increase of temperature. Passage of direct current through ionic solution over a prolonged period can lead to the change in its composition due to electrochemical reactions. Measurement of the conductivity of ionic solutions. Accurate measurement of an unknown resistance can be performed on a Wheaton bridge. However, for measuring the resistance of an ionic solution, we face two problems. Firstly, passing direct current, that is DC, changes the composition of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. The first difficulty is resolved by using an alternative current, that is AC source of power. The second problem is solved by using a specially designed vessel called conductivity cell. It is available in several designs. Basically, it consists of two platinum electrodes coated with platinum black, that is finely divided metallic PT, is deposited on the electrodes electrochemically. These have area of cross section equal to A and are separated by distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross section A. In such a column, the length L and the area of cross section are A. The resistance of such a column of solution is then given by the equation R is equal to rho into L upon A is equal to L upon Ka, that is equation 17. The quantity L upon A is called cell constant, denoted by the symbol G star. It depends on the distance between the electrodes and their area of cross section and has the dimension of length and can be calculated if we know L and A. Measurement of L and A is not only inconvenient but also unreliable. The cell constant is usually determined by measuring the resistance of cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations and at different temperatures. The cell constant G star is then given by the equation G star is equal to L upon A is equal to RK, that is equation 18. Conductivity and molar conductivity of KCl solutions at 298.15 Kelvin. Concentration or molarity, conductivity, molar conductivity. Concentration or molarity, mole per liter 1.000, mole per meter cube 1000. Conductivity, Siemens per centimeter 0.1113, Siemens per meter 11.13. Molar conductivity, Siemens centimeter square per mole 111.3, Siemens meter square per mole 111.3 into 10 raised to minus 4. Concentration molarity, mole per liter 0.100, mole per meter cube 100.0. Conductivity, Siemens per centimeter 0.0129, Siemens per meter 1.29. Molar conductivity, Siemens centimeter square per mole 129.0, Siemens meter square per mole 129.0 into 10 raised to minus 4. Concentration molarity, mole per liter 0.010, mole per meter cube 10.00. Conductivity, Siemens per centimeter 0.00141, Siemens per meter 0.141. Molar conductivity, Siemens centimeter square per mole 141.0, Siemens meter square per mole 141.0 into 10 raised to minus 4. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for the measurement of the resistance is shown in figure. It consists of two resistance R3 and R4, a variable resistance R1 and the conductivity cell having the unknown resistance R2. The Wheaton bridge is fed by an oscillator O, that is a source of AC power in the audio frequency range 550 to 5000 cycles per second. P is a suitable detector, that is a headphone or other electronic device, and the bridge is balanced when no current passes through the detector. Under these conditions, unknown resistance R2 is equal to R1 into R4 upon R3, that is equation 19. These days, inexpensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation K is equal to cell constant upon R is equal to G star upon R, that is equation 20. The conductivity of solutions of different electrolytes in the same solvent and at a given temperature differs due to charge and size of the ions in which they dissociate, the concentration of ions or ease with which the ions move under a potential gradient. It therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, denoted by the symbol lambda m. It is related to the conductivity of the solution by the equation molar conductivity is equal to lambda m is equal to K upon C, that is equation 21. In the above equation, if K is expressed in Siemens per meter and the concentration C in mole per meter cube, then the unit of lambda m are in Siemens meter square per mole. It may be noted that 1 mole per meter cube is equal to 1000, that is liter per meter cube, into molarity, that is mole per liter, and hence lambda m, that is Siemens centimeter square per mole, is equal to K, that is Siemens per centimeter upon 1000 liter per meter cube into molarity, that is mole per liter. If we use Siemens per centimeter as the unit for K and mole per centimeter cube, the units of concentration, then the unit for lambda m are Siemens centimeter square per mole, it can be calculated by using the equation lambda m, that is Siemens centimeter square per mole, is equal to K, that is Siemens per centimeter into 1000, that is centimeter cube per liter, upon molarity, that is mole per liter. Both type of units are used in literature and are related to each other by the equations 1. Siemens meter square per mole is equal to 10 raised to 4 Siemens centimeter square per mole, or 1 Siemens centimeter square per mole 10 raised to minus 4 Siemens meter square per mole. Example 4. Resistance of a conductivity cell filled with 0.1 mole per liter KCl solution is 100 ohm. If the resistance of the same cell when filled with 0.02 mole per liter KCl solution is 520 ohm, calculate the conductivity and molar conductivity of 0.02 mole per liter KCl solution. The conductivity of 0.1 mole per liter KCl solution is 1.29 Siemens per meter. Solution. The cell constant is given by the equation cell constant is equal to G star is equal to conductivity into resistance is equal to 1.29 Siemens per meter into 100 ohm is equal to 129 per meter is equal to 1.29 per centimeter. Conductivity of 0.02 mole per liter KCl solution is equal to cell constant upon resistance is equal to G star upon R is equal to 129 per meter upon 520 ohm is equal to 0.248 Siemens per meter. Concentration is equal to 0.02 mole per liter is equal to 1000 into 0.02 mole per meter cube is equal to 20 mole per meter cube. Molar conductivity is equal to lambda m is equal to K upon C is equal to 248 into 10 raised to minus 3 Siemens per meter upon 20 mole per meter cube is equal to 124 into 10 raised to minus 4 Siemens meter square per mole. Alternatively, K is equal to 1.29 per centimeter upon 520 ohm is equal to 0.248 into 10 raised to minus 2 Siemens per centimeter, and lambda m is equal to K into 1000 centimeter cube per liter molarity is equal to 0.248 into 10 raised to minus 2 Siemens per centimeter into 1000 centimeter cube per liter upon 0.02 mole per liter is equal to 124 Siemens centimeter square per mole. Example 5. The electrical resistance of a column of 0.05 mole per liter NaOH solution of diameter 1 cm and length 50 cm is 5.55 into 10 raised to 3 ohm. Calculate its resistivity, conductivity and molar conductivity. Solution. A is equal to pi r square is equal to 3.14 into 0.5 square centimeter square is equal to 0.785 centimeter square is equal to 0.785 into 10 raised to minus 4 meter square. L is equal to 50 centimeter is equal to 0.5 meter. R is equal to rho L upon A, or rho is equal to RA upon L is equal to 5.55 into 10 raised to 3 ohm into 0.785 centimeter square upon 50 centimeter is equal to 87.135 ohm centimeter. Conductivity is equal to K is equal to 1 upon rho is equal to 1 upon 87.135 Siemens per centimeter is equal to 0.01148 Siemens per centimeter. Molar conductivity lambda m is equal to K into 1000 upon C centimeter cube per liter is equal to 0.01148 Siemens per centimeter into 1000 centimeter cube per liter upon 0.05 mole per liter is equal to 229.6 Siemens centimeter square per mole. If we want to calculate the values of different quantities in terms of meter instead of centimeter, rho is equal to RA upon L is equal to 5.55 into 10 raised to 3 ohm into 0.785 into 10 raised to minus 4 meter square upon 0.5 meter is equal to 87.135 into 10 raised to minus 2 ohm meter. K is equal to 1 upon rho is equal to 100 upon 87.135 ohm meter is equal to 1.148 Siemens per meter, and lambda m is equal to K upon C is equal to 1.148 Siemens per meter upon 50 mole per meter cube is equal to 229.6 into 10 raised to minus 4 Siemens meter square per mole. Variation of conductivity and molar conductivity with concentration. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration of both for weak and strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution is decreases on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. This is clear from the equation G is equal to Ka upon L is equal to K. That is, both A and L are unity in their appropriate units in meter or centimeter. Molar conductivity of a solution at a given concentration is the conductance of the volume V of a solution containing 1 mole of electrolyte kept between two electrodes with an area of cross section A and distance of unit length L. Therefore, lambda m is equal to Ka upon L is equal to K. Since L is equal to 1 and A is equal to V, that is volume containing 1 mole of electrolyte, lambda m is equal to Kv, that is equation 22. Molar conductivity increases with decrease in concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. It has been found that decrease in K on dilution of a solution is more than compensated by increase in its volume. Physically, it means that at a given concentration, lambda m can be defined as the conductance of the electrolyte solution kept between the electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. When concentration approaches 0, the molar conductivity is known as limiting molar conductivity and is represented by the symbol lambda m0. The variation in lambda m with concentration is different for strong and weak electrolytes. Strong electrolytes. For strong electrolytes, lambda m increases slowly with dilution and can be represented by the equation lambda m is equal to lambda m0 minus A into C raised to 1 upon 2. That is equation 23. It can be seen that if we plot lambda m against C raised to 1 upon 2, we obtain a straight line with intercept equal to lambda m0 and slope equal to minus A. The value of the constant A for a given solvent and temperature depends on the type of electrolyte. That is, the charges on the cation and anion produced on the dissociation of the electrolyte in the solution. Thus, NaCl, CaCl2, MgSO4 are known as 1,1, 2,1 and 2,2 electrolytes respectively. All electrolytes of a particular type have the same value for A. Example 6. The molar conductivity of KCl solutions at different concentrations at 298 Kelvin are given below. Conductivity mole per liter, lambda m Siemens centimeter square per mole. Conductivity 0.000198, lambda m 148.61. Conductivity 0.000309, lambda m 148.29. Conductivity 0.000521, lambda m 147.81. Conductivity 0.000989, lambda m 147.09. Show that a plot between lambda m and C raised to 1 upon 2 is a straight line. Determine the values of lambda m0 and A for KCl. Solution. Taking the square root of concentration, we obtain conductivity raised to 1 upon 2 mole per liter raised to 1 upon 2 lambda m Siemens centimeter square per mole. Conductivity raised to 1 upon 2 0.01407 lambda m 148.61. Conductivity raised to 1 upon 2 0.01758 lambda m 148.29. Conductivity raised to 1 upon 2 0.02283 lambda m 147.81. Conductivity raised to 1 upon 2 0.03145 lambda m 147.09. A plot of lambda m, that is y-axis, and c raised to 1 upon 2, that is x-axis, is shown in figure. It can be seen that it is nearly a straight line. From the intercept, that is c raised to 1 upon 2 is equal to 0, we find that lambda m0 is equal to 150.0 Siemens centimeter square per mole, and a is equal to minus slope is equal to 87.46 Siemens centimeter square per mole, or mole per liter raised to 1 upon 2. Kohlrausch examined lambda m0 values for a number of strong electrolytes and observed certain regularities. He noted that the difference in lambda m0 of the electrolytes NaX and Kx for NEX is nearly constant. For example, at 298 Kelvin, lambda m0 KCl minus lambda m0 NaCl is equal to lambda m0 KBr minus lambda m0 NABr is equal to lambda m0 KL minus lambda m0 NaL approximately equals to 23.4 Siemens centimeter square per mole. And similarly, it was found that lambda m0 NABr minus lambda m0 NaCl is equal to lambda m0 KBr minus lambda m0 KCl approximately equals to 1.8 Siemens centimeter square per mole. On the basis of the above observations, he enunciated Kohlrausch Law of independent migration of ions. The law stated that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Thus, if lambda Na plus 0 and lambda Cl minus 0 are limiting molar conductivity of the sodium and chloride ions respectively, then the limiting molar conductivity for sodium chloride is given by the equation lambda m0 NaCl is equal to lambda Na plus 0 plus lambda Cl minus 0, that is equation 24. In general, if an electrolyte on dissociation gives V plus cations and V minus anions, then its limiting molar conductivity is given by lambda m0 is equal to V plus lambda plus 0 plus V minus lambda minus 0, that is equation 25. Here lambda plus 0 and lambda minus 0 are the limiting molar conductivities of the cation and anion respectively. The values of lambda 0 for some cations and anions at 298 Kelvin are given in table. Table limiting molar conductivity for some ions in water at 298 Kelvin. Ion lambda 0 Siemens centimeter square per mole. Ion lambda 0 Siemens centimeter square per mole. Ion H plus lambda 0 349.6. Ion OH minus lambda 0 199.1. Ion Na plus lambda 0 50.1. Ion Cl minus lambda 0 76.3. Ion K plus lambda 0 73.5. Ion Br minus lambda 0 78.1. Ion Ca2 plus lambda 0 119.0. Ion CH3COO minus lambda 0 40.9. Ion Mg2 plus lambda 0 106.0. Ion SO4 2 minus lambda 0 160.0. Weak electrolytes. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentrations, and hence for such electrolytes the change in lambda m with dilution is due to increase in the degree of dissociation and consequently the number of ions in the total volume of solution that contains 1 mole of electrolyte. In such cases, lambda m increases steeply on dilution. especially near lower concentration. Therefore, lambda m0 cannot be obtained by extrapolation of lambda m to zero concentration. At infinite dilution, that is, concentration C becomes zero, electrolyte dissociates completely, that is, alpha is equal to 1. But at such low concentration, the conductivity of the solution is so low that it cannot be measured accurately. Therefore, lambda m0 for weak electrolytes is obtained by using Kohlrausch law of independent migration of ions. At any concentration C, if alpha is the degree of dissociation, then it can be approximated to the ratio of molar conductivity lambda m at the concentration C to limiting molar conductivity lambda m0. Thus we have alpha is equal to lambda m upon lambda m0, that is equation 26. But we know that for a weak electrolyte like acetic acid, Ka is equal to C alpha square upon 1 minus alpha is equal to C lambda m square upon lambda m0 square into 1 minus lambda m upon lambda m0 is equal to C lambda m square upon lambda m0 into lambda m0 minus lambda m. That is equation 27. Applications of Kohlrausch law. Using Kohlrausch law of independent migration of ions, it is possible to calculate lambda m0 for any electrolyte from the lambda 0 of individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the lambda m0 and lambda m at a given concentration C. Example 7. Calculate lambda m0 for CaCl2 and MgSO4 from the data given in table. Solution. We know from Kohlrausch law that lambda m0 CaCl2 is equal to lambda Ca2 plus 0 plus 2 lambda Cl minus 0 is equal to 119.0 Siemens centimeter square per mole plus 2 into 76.3 Siemens centimeter square per mole is equal to 119.0 plus 152.6 Siemens centimeter square per mole is equal to 271.6 Siemens centimeter square per mole. Lambda m0 MgSO4 is equal to lambda mg2 plus 0 plus lambda SO4 2 minus 0 is equal to 106.0 Siemens centimeter square per mole plus 160.0 Siemens centimeter square per mole is equal to 266 Siemens centimeter square per mole. Example 8. Lambda m0 for NaCl, HCl and NaAC are 126.4, 425.9 and 91.0 Siemens centimeter square per mole respectively. Calculate lambda 0 for HAC. Solution. Lambda m0 HAC is equal to lambda h plus 0 plus lambda AC minus 0 is equal to lambda h plus 0 plus lambda Cl minus 0 plus lambda AC minus 0 plus lambda Na plus 0 minus lambda Cl minus 0 minus lambda Na plus 0 is equal to lambda m0 HCl plus lambda m0 NaAC minus lambda m0 NaCl is equal to 425.9 plus 91.0 minus 126.4 Siemens centimeter square per mole is equal to 390.5 Siemens centimeter square per mole. Example 9. The conductivity of 001028 mole per liter acetic acid is 4.95 into 10 raised to minus 5 Siemens per centimeter. Calculate its dissociation constant if lambda m0 for acetic acid is 390.5 Siemens centimeter square per mole. Solution. Lambda m is equal to K upon C is equal to 4.95 into 10 raised to minus 5 Siemens per centimeter upon 0.001028 mole per liter into 1000 centimeter cube upon liter is equal to 48.15 Siemens centimeter square per mole. Alpha is equal to lambda m upon lambda m0 is equal to 48.15 Siemens centimeter square per mole upon 390.5 Siemens centimeter square per mole is equal to 0.1233. K is equal to C alpha square upon 1 minus alpha is equal to 0.001028 mole per liter into 0.1233 square upon 1 minus 0.1233 is equal to 1.78 into 10 raised to minus 5 mole per liter. Electrolytic cells and electrolysis. In an electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical processes are of great importance in the laboratory and the chemical industries. One of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. If a DC voltage is applied to the two electrodes, then Cu2 plus ions discharge at the cathode, that is negatively charged, and the following reaction takes place. Cu2 plus aqueous plus 2E minus, it gives Cu solid, that is equation 28. Copper metal is deposited on the cathode. At the anode, copper is converted into Cu2 plus ions by the reaction. Cu solid, it gives Cu2 plus solid plus 2E minus, that is equation 29. Thus, copper is dissolved, that is oxidized at anode, and deposited, that is reduced at cathode. This is the basis for an industrial process in which impure copper is converted into copper of high purity. The impure copper is made an anode that dissolves on passing current, and pure copper is deposited at the cathode. Many metals like Na, Mg, Al, etc. are produced on large scale by electrochemical reduction of their respective cations where no suitable chemical reducing agents are available for this purpose. Sodium and magnesium metals are produced by the electrolysis of their fused chlorides, and aluminum is produced by electrolysis of aluminum oxide in presence of cryolite. Quantitative aspects of electrolysis. Michael Faraday was the first scientist who described the quantitative aspects of electrolysis. Faraday's laws of electrolysis. After his extensive investigations on electrolysis of solutions and melts of electrolytes, Faraday published his results during 1833 to 34 in the form of the following well-known Faraday's two laws of electrolysis. 1. First law. The amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of the electricity passed through the electrolyte, that is, solution or melt. 2. Second law. The amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights, that is, atomic mass of metal divided by number of electrons required to reduce the cation. There were no constant current sources available during Faraday's times. The general practice was to put a coulometer, that is a standard electrolytic cell, for determining the quantity of electricity passed from the amount of metal, that is generally silver or copper, deposited or consumed. However, coulometers are now obsolete and we now have the constant current, that is I. Sources available and the quantity of electricity Q passed is given by Q is equal to I into T. Q is in coulombs when I is in ampere and T is in second. The amount of electricity, that is or charge, required for oxidation or reduction depends on the stoichiometry of the electrode reaction. For example, in the reaction Ag plus aqueous plus E minus, it gives Ag solid, that is equation 30. 1 mole of the electron is required for the reduction of 1 mole of silver ions. We know that charge on 1 electron is equal to 1.6021 into 10 raised to minus 19 coulomb. Therefore, the charge on 1 mole of electrons is equal to Na into 1.6021 into 10 raised to minus 19 coulomb is equal to 6.02 into 10 raised to 23 per mole into 1.6021 into 10 raised to minus 19. Coulomb is equal to 96,487 coulomb per mole. This quantity of electricity is called Faraday and is represented by the symbol F. For approximate calculations, we use 1 Faraday is approximately equals to 96,500 coulomb per mole. For the electrode reactions, Mg2 plus liquid plus 2E minus, it gives Mg solid, that is equation 31. Al3 plus liquid plus 3E minus, it gives Al solid. That is equation 32. It is obvious that 1 mole of Mg2 plus and Al3 plus require 2 mole of electrons, that is 2F, and 3 mole of electrons, that is 3F respectively. The charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and time in seconds. In commercial production of metals, current as high as 50,000 amperes are used, that amounts to about 0.518 Faraday per second. Example 10. A solution of CuSO4 is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at the cathode? Solution. T is equal to 600 seconds. Charge is equal to current into time is equal to 1.5 ampere into 600 seconds is equal to 900 coulomb. According to the reaction, Cu2 plus aqueous plus 2E minus, it gives Cu solid. We require 2 Faraday or 2 into 96,487 coulomb to deposit 1 mole or 63 gram of Cu. For 900 coulomb, the mass of Cu deposited is equal to 63 gram per mole into 900 coulomb upon 2 into 96,487 coulomb per mole is equal to 0.2938 gram. Products of electrolysis. Products of electrolysis depend on the nature of material being electrolyzed and the type of electrodes being used. If the electrode is inert, that is platinum or gold, it does not participate in the chemical reaction and acts only as source or sink for electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction. Thus, the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis depend on the different oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Moreover, some of the electrochemical processes, although feasible, are so slow kinetically that at lower voltages this do not seem to take place. An extra potential, that is called overpotential, has to be applied, which makes such process more difficult to occur. For example, if we use molten NaCl, the products of electrolysis are sodium metal and Cl2 gas. Here we have only one cation, that is Na+, which is reduced at the cathode, that is Na++ plus E-, it gives Na, and one anion, that is Cl-, which is oxidized at the anode, that is Cl-, it gives 1/2 Cl2 plus E-. During the electrolysis of aqueous sodium chloride solution, the products are NaOH, Cl2 and H2. In this case, besides the Na+ and Cl- ions, we also have H+ and OH- ions along with the solvent molecules H2O. At the cathode, there is competition between the following reduction reactions. Na plus aqueous plus E-, it gives Na solid. E standard electrode potential cell is equal to minus 2.71 volt. H plus aqueous plus E-, it gives 1/2 H2 gaseous. E standard electrode potential cell is equal to 0.00 volt. The reaction with higher value of E standard electrode potential is preferred, and therefore the reaction at cathode during electrolysis is H plus aqueous plus E-, it gives 1/2 H2 gaseous, that is equation 33. But H plus aqueous is produced by the dissociation of H2O, that is H2O liquid, it gives H plus aqueous plus OH- aqueous, that is equation 34. Therefore, the net reaction at the cathode may be written as the sum of 33 and 34, and we have H2O liquid plus E-, it gives 1/2 H2 gaseous plus OH-, that is equation 35. At the anode, the following oxidation reactions are possible. Cl- aqueous, it gives 1/2 Cl2 gaseous plus E-. E standard electrode potential cell is equal to 1.36 volt, that is equation 36. 2H2O liquid, it gives O2 gaseous plus 4H plus aqueous plus 4E minus. E standard electrode potential cell is equal to 1.23 volt. That is equation 37. The reaction at anode with lower value of E standard electrode potential is preferred, and therefore water should get oxidized in preference to Cl minus aqueous. However, on account of overpotential of oxygen, reaction 36 is preferred. Thus, the net reactions may be summarized as NaCl aqueous. In presence of H2O, it gives Na plus aqueous plus Cl minus aqueous. Cathode, H2O liquid plus E minus, it gives 1 upon 2 H2 gaseous plus OH minus aqueous. Anode, Cl minus aqueous, it gives 1 upon 2 Cl2 gaseous plus E minus. Net reaction, NaCl aqueous plus H2O liquid, it gives Na plus aqueous plus OH minus aqueous plus 1 upon 2 H2 gaseous plus 1 upon 2 Cl2 gaseous. The standard electrode potential are replaced by electrode potentials given by Nernst equation to take into account the concentration effects. During the electrolysis of sulfuric acid, the following processes are possible at the anode. 2H2O liquid, it gives O2 gaseous plus 4H plus aqueous plus 4E minus. E standard electrode potential cell is equal to plus 1.23 volt. That is equation 38. To SO4 2 minus aqueous, it gives S2O8 2 minus aqueous plus 2E minus. E standard electrode potential cell is equal to 1.96 volt. That is equation 39. For dilute sulfuric acid, reaction 38 is preferred, but at higher concentrations of H2SO4, reaction 39 is preferred. Batteries. Any battery, that is, actually it may have one or more than one cell connected in series, or cell that we use as a source of electrical energy, is basically a galvanic cell where the chemical energy of the redox reaction is converted into electrical energy. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. There are mainly two types of batteries. 1. Primary batteries. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type is the dry cell, that is known as Planck cell after its discoverer, which is used commonly in our transistors and clocks. The cell consists of a zinc container that also acts as anode, and the cathode is a carbon, that is graphite rod, surrounded by powdered manganese dioxide and carbon. The space between the electrodes is filled by a moist paste of ammonium chloride, that is NH4Cl, and zinc chloride, ZnCl2. The electrode reactions are complex, but they can be written approximately as follows. Anode, Zn solid, it gives Zn2 plus 2E minus. Cathode, MnO2 plus NH4 plus E minus, it gives MnOOH plus NH3. In the reaction at cathode, manganese is reduced from the +4 oxidation state to the +3 state. Ammonia produced in the reaction forms a complex with Zn2 plus to give ZnNH3 2 plus. The cell has a potential of nearly 1.5 volt. Mercury cell, suitable for low current devices like hearing aids, watches, etc., consists of zinc mercury amalgam as anode and a paste of HgO and carbon as the cathode. The electrolyte is a paste of KOH and ZnO. The electrode reactions for the cell are given below. Anode, ZnHg plus 2OH minus, it gives ZnO solid plus H2O plus 2E minus. Cathode, HgO plus H2O plus 2E minus, it gives Hg liquid plus 2OH minus. The overall reaction is represented by ZnHg plus HgO solid, it gives ZnO solid plus Hg liquid. The cell potential is approximately 1.35 volt. and remains constant during its life, as the overall reaction does not involve any ion in a solution whose concentration can change during its lifetime. 2. Secondary batteries. A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage battery, commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with lead dioxide, that is PbO2, as cathode. A 38% solution of sulfuric acid is used as an electrolyte. The cell reactions when the battery is in use are given below. Anode Pb solid plus SO4 2- aqueous, it gives PbSO4 solid plus 2E-. Cathode PbO2 solid plus SO4 2- aqueous plus 4H plus aqueous plus 2E-, it gives PbSO4 solid plus 2H2O liquid. That is, overall cell reaction consists of cathode and anode reactions is Pb solid plus PbO2 solid plus 2H2SO4 aqueous, it gives 2PbSO4 solid plus 2H2O liquid. On charging the battery, the reaction is reversed and PbSO4 solid on anode and cathode is converted into Pb and PbO2 respectively. Another important secondary cell is the nickel-cadmium cell, which has longer life than the lead storage cell but more expensive to manufacture. We shall not go into detail of working of the cell and the electrode reaction during charging and discharging. The overall reaction during discharge is Cd solid plus 2Ni OH thrice solid, it gives CdO solid plus 2Ni OH twice solid plus H2O liquid. Fuel cells. Production of electricity by thermal plants is not a very efficient method and is a major source of pollution. In such plants, the chemical energy, that is heat of combustion of fossil fuels, that is coal, gas or oil, is first used for converting water into high pressure steam. This is then used to run a turbine to produce electricity. We know that a galvanic cell directly converts chemical energy into electricity and is highly efficient. It is now possible to make such cells in which reactants are fed continuously to the electrodes and products are removed continuously from the electrolyte compartment. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. One of the most successful fuel cells uses the reaction of hydrogen with oxygen to form water. The cell was used for providing electrical power in the Apollo space program. The water vapors produced during the reaction were condensed and added to the drinking water supply for the astronauts. In the cell, hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous sodium hydroxide solution. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of electrode reactions. The electrode reactions are given below. Cathode O2 gaseous plus 2H2O liquid plus 4E-, it gives 4OH- aqueous. Anode 2H2 gaseous plus 4OH- aqueous, it gives 4H2O liquid plus 4E-. Overall reaction being 2H2 gaseous plus O2 gaseous, it gives 2H2O liquid. The cell runs continuously as long as the reactants are supplied. Fuel cells produce electricity with an efficiency of about 70% compared to the thermal plants whose efficiency is about 40%. There has been tremendous progress in the development of new electrode materials, better catalysts, and electrolytes for increasing the efficiency of fuel cells. These have been used in automobiles on an experimental basis. Fuel cells are pollution-free, and in view of their future importance, a variety of fuel cells have been fabricated and tried. Corrosion. Corrosion slowly coats the surface of metallic objects with oxides or other salts of the metal. The rusting of iron, tarnishing of silver, Development of green coating on copper and bronze are some of the examples of corrosion. It causes enormous damage to buildings, bridges, ships, and to all objects made of metals, especially that of iron. We lose crores of rupees every year on account of corrosion. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxides. Corrosion of iron, that is commonly known as rusting, occurs in presence of water and air. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomenon. At a particular spot of an object made of iron, oxidation takes place and that spot behaves as anode, and we can write the reaction anode 2Fe solid, it gives 2Fe2 plus 4E minus. E standard electrode potential Fe2 plus Fe is equal to minus 0.44 volt. Electrons released at anodic spot move through the metal and go to another spot on the metal and reduce oxygen in the presence of H+, that is, which is believed to be available from H2CO3 formed due to the dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. This spot behaves as cathode with the reaction cathode O2 gaseous plus 4H plus aqueous plus 4E minus, it gives 2H2O liquid. E standard electrode potential H plus change in state O2 change in state H2O is equal to 1.23 volt. The overall reaction being 2Fe solid plus O2 gaseous plus 4H plus aqueous, it gives 2Fe2 plus aqueous plus 2H2O liquid. E standard electrode potential cell is equal to 1.67 volt. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which come out as rust in the form of hydrated ferric oxide, that is Fe2O3 into XH2O, and with further production of hydrogen ions. Prevention of corrosion is of prime importance. It not only saves money but also helps in preventing accidents such as a bridge collapse or failure of a key component due to corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of the metallic object to come in contact with atmosphere. This can be done by covering the surface with paint or by some chemicals, that is bisphenol. Another simple method is to cover the surface by other metals, that is Sn, Zn, etc. that are inert or react to save the object. An electrochemical method is to provide a sacrificial electrode of another metal, that is like Mg, Zn, etc., which corrodes itself but saves the object.